Okay, so we're very happy to be back at MOPA for the first session in the new year with Albert Visser from, and I cannot pronounce this, I'm sorry, Utrecht University?
Utrecht.
Utrecht, sorry. Speaking on interpreters as a species of consistoids. Thank you, Albert.
Right. Okay, thank you very much for the introduction. I'm also quite happy to speak in this nice seminar. Yeah, so the material I'm going to present is growing all the time, and so I'm only going to be able to show you some part of it. So I think I choose the stuff that would be most interesting for the people of this seminar, but so there is still more, and I will have some pointers on what there is more. Okay, so yeah, so what first? Let me first say something about the aims. So yeah, so one of the main aims is this whole idea of getting rid of arithmetization. So the statements in Gödelian meta-mathematics really have both the kind of dependence on design choices that all mathematical results have, but they also have dependence on design choices at the object level. So that's a kind of second level of design choices, and the idea is to eliminate these design choices. So to eliminate as I say it here, the non-mathematical quantifier over implementation choices that you see, for example, in statement of the second incompleteness here. But so that's more or less my broadly philosophical motivation. But I think there's a kind of much more exciting side to the thing, because the coordinate-free definitions are applicable in places where you actually do not have the resources to do arithmetization, and so something new will happen. And I think it's exciting to see what that new thing will be. And also, I guess maybe the wider context, so where we have things like consistency statements and no arithmetization, could throw some light on the familiar world where we do have the possibility of arithmetization. So that's very roughly the aim. And so, Harvey Friedman and I have been thinking about this kind of problem in parallel. And so, but yeah, sometimes Harvey comes up with something extremely simple that I didn't think of, and so that idea is the starting point of the present development. And so here is Harvey's argument. So suppose that we have a finitely axiomatized theory A, and then we have that for all B, for all arithmetical sentences B, if Peano plus B interprets A, then Peano plus B proves the consistency of A. Sorry, not then, if and only if, right? So the interpreting A is the same as the consistency of A over Peano plus B, and that for all B. And so this tells us, in fact, that the consistency statement is the weakest statement that interprets A over PA. And with that, the consistency statement has been characterized modulo PA provability. Now, of course, so in some sense, I guess Harvey's result is not such a good result, because PA provable equivalence is not such a fine equivalence relation, and I will show you how to improve it to EA, so elementary arithmetic provable equivalence, but that's for somewhat later. So let's first now concentrate on the proof. So let's start from on the left-hand side. So suppose PA plus B interprets A. So this means, of course, since A is finitely axiomatized, of course, the interpretation will happen already in a finite part of PA plus B. And so there will be some PA theorem D such that D plus B interprets A. But now D plus B interprets A. So since A is finite, it's a finite statement. And so it's a sigma 0, 1 statement, and so by sigma completeness PA will prove it, right? So PA will prove that D plus B interprets A. But then, of course, since interpretability implies relative consistency, Peano will prove that the consistency of D plus B implies the consistency of A. Yeah, I use modal notations, right? So this, so the diamond really means consistency over D plus B of true. So yeah, in fact, the consistency of D plus B. Now, PA, now this is the important step. PA is essentially reflexive, and so it proves the consistency of every finite, every finite every RE extension of PA proves the consistency of all its finite subseries. So PA plus B proves the consistency of D plus B, but that's the antecedent of the previous sentence, and so PA plus B proves the consistency of A. Right, so that's from left to right. Is this clear? Because this whole argument, so the whole building is in fact constructed upon this reasoning, so it's important that you get all the steps. And now the other direction is the interpretation existence lemma. From a consistency statement we can construct an interpretation, so we can go from right to left, right? So that's the main reasoning. So it's an extremely simple reasoning, but the idea is the idea is in this this very good statement of what's going on. Yeah.
So this from right to left. So that's the arithmetized completeness.
That's the arithmetized completeness here. Yes, precisely. Yeah. So and it's important. So if people, so I'm not going to say anything about category theory, but in fact, this tells you that PA plus con A interprets A as a universal arrow in the right categories, right? So you can understand everything what is going on here in a categorical framework, but the framework is just a kind of way the categorical framework is just a kind of way to link it to known concepts, but in fact for it's not for our talk, for this talk, it's not really needed to embed it in the categorical framework. Okay, so what does the, so now what I'm going to do is to abstract away from this idea, and so the question I'm going to address is really, so what property of PA is it that makes the whole argument tick? And so so consider any theory U. So I'm always assuming finite signature, but the theory U can in this case have any complexity. It need not be RE or anything. And look at the finitely axiomatized A. So then we say that the sentence C such that satisfies this universal arrow principle. So U plus B implies C if and only U plus B interprets A. So for all U sentences B, I call that an interpreter, right? So that the C in the case of PA was con PA, right? So that's the property that we're talking about. So yeah, modulo U provable equivalency then is the weakest U sentence B, such that U plus B interprets A. So and again, so U plus C interprets B is a universal arrow in the appropriate categories. So that from the universality, it really follows that C is unique with the described property modulo U-provable equivalence. So I will use a suggestive notation. So really con A modal notation for this C, right? So I always use a kind of column function. So we choose, of course, because the whole thing is only determined up to U-provable equivalence, and so I use this double diamond as a kind of column function that selects something from the equivalence class. But it's quite a good heuristic, at least, to have this notation. But it's important also to keep in mind that it really selects something from an equivalence class, so it's not really, it's only uniquely determined modulo provable equivalence. Now, so these interpreters, yeah, I call that consistoids. That means that they really behave like consistency statements with respect to interpretation power. But as we will see, so in a broader context, they're not always consistency statement, but could be something new. Now the theory is Friedman, I call that Friedman reflexive. If every finitely axiomatized A has an interpreter, diamond A or double diamond A over U, right? So that it's simply that you always have an interpreter for every A. And we call it effectively Friedman reflexive if there is an effective way of finding these double diamonds. So, yeah, it's important.
Sorry. So this finite axiomatizability will be carried over all the time, or?
Yeah. Okay. Yeah. So that's so I'm not going to address this problem, right? So the whole approach works for finitely axiomatized series, and so you could ask, so what we want RE series. Yeah. So there are really two plans to overcome that restriction, but so yeah, one plan is really to look at sets of sentences instead of single ones for the consistoids or the interpreters, and the other one is to use finite approximations of the given series. So in the case of PA, there's a very good solution. So we can get provability in PA by simply using the finite series ACA0 as its stand-in, right? So I have several ideas of how to extend the approach to the RE case, but yeah, I'm now only talking about yeah this approach towards finite series.
Thank you.
Yeah, good question. And so yeah, and so effectively Friedman reflexive. So there is also important, of course. So that means that there are effective choices of representatives of an equivalence class, right? So the other choices could be very non-effective. Now there are some easy facts. So if we have any series and we extend it in the same language, I really use for series, I use the subset notation from extension in the same language. So it's not, you're not allowed to expand the signature too. So if we expand in the same language, Friedman reflexivity is preserved. Yeah, so maybe, so one heuristic, of course, so Friedman reflexivity is a kind of piano likeness, right? So the series behave a little bit like piano in certain respects. And so as you know, that if you extend piano by some RE series, that really preserves lots of the properties of piano, like being essentially reflexive, etc. So we have that if A interprets B, then U proves that the interpreter of A implies the interpreter of B. Of course, that's just a general property of universal arrows. And we have the commutation with disjunction. And interestingly, so the commutation with disjunction is not a universal property. So here you have a small, you have the proof, right? So from right to left is easy because of the second item here, right? So if A interprets B, then you have that you have the interpretation, the implication between the interpreters, and so that then you have, of course, that the double diamond of A will imply the double diamond of A or B, right? Because A or B is weaker, and the same for this one, right? So this follows by the earlier stuff, but this one is more interesting. So let EA be the conjunction of the axioms of identity for the signature of A, including the axiom exists X, X is X. Yeah, so that we need this EA because there's kind of bit of a naturality in the way that we treat interpretations. So the whole thing is that in predicate logic, we treat identity as a logical connective, point one. But in interpretations, we do not do that. We allow translating identity to an equivalence relation. And the whole thing is that that then you have to take the axioms of identity, add them to the theory. So they should also be, the translations of these things should also work, right? So so now we have that U plus the interpreter of A or B interprets A or B. This means that we can find a translation tau such that A plus the double diamond of A or B derives the EA, the conjunction of EA with this disjunction translated, right? That's precisely what it is to say that you have an interpretation. And now since translations commute with the propositional connectives, we get this, and clearly this thing, if we add EA plus A tau to U, we can interpret A, because this really tells us that there is an interpretation of A, and then hence by the universal property again, it will imply the double diamond of A, and similarly this one will imply the double diamond of B, right? So that's the commutation with disjunction. Okay, so yeah, now one would hope, of course, that all theories are Friedman reflexive, but that's definitely not the case. So here you have an argument that S12 is not Friedman reflexive. So, but it's also an argument that I sigma 1 is not sigma reflexive, and ACA 0 is not Friedman reflexive, and Gödel-Bernays set theory is not Friedman reflexive, etc. So then no finitely axiomatized, consistent, sequential theory is Friedman reflexive. Now suppose it were. Now we can always find a consistent A that is not interpreted by the theory, right? So, well, maybe, for example, the theory plus its own consistency would do the trick. Then, so then the theory, that means that the theory will not prove its own, the consistoid of A, and so the theory plus the negation will be consistent. That's it. Where does the music come from? Okay, but also on the other hand, for all definable cuts in S12, we have that S12 plus the consistency of A relativized to I will interpret A, and so by the universal property, it will follow that every one of the relativized consistency statements will prove the double diamond of A, and so by contraposing S12 plus the negation of the double diamond of A will prove that the inconsistency of A for all definable cuts, right? And so this is this consistent theory. We proved that, right? And now the important point is that finitely axiomatized, finitely axiomatized series cannot do that. They cannot prove a sigma-1 sentence on all definable cuts without providing an actual finite witness. And so there's a theorem due to Harvey and to Jan Krajicek that tells us that if a consistent finitely axiomatized sequential series proves the inconsistency for all I, then the thing is in fact inconsistent, but we had assumed that it's not so, a contradiction. And so, for example, S12 is not Friedman reflexive. But we have, of course, that this is just an example, but we have a much stronger result. So suppose that V and W are locally reconciled. Oh, sorry, I first want to define what reconcilability is. So V and W are reconcilable if there you can find sentences DE in the respective languages such that V plus D is consistent and V plus D is mutually interpretable with W plus E, right? So the whole thing is that, so they are reconcilable if you can extend them both finitely in such a way that you get mutually interpretable things. And now, so suppose that U is consistent and Friedman reflexive. So what we then have is that, well, first we have that if you, I see I repeated something. So first we have that that U cannot be, in the case U is sequential, so if it has sequence coding, then it cannot be axiomatizable by a set of axioms of restricted complexity. So I argued already that it cannot be finitely axiomatized in the previous slide, but it cannot even be axiomatized by a set of restricted complexity. So for example, primitive recursive arithmetic is also not going to be Friedman reflexive. And the other thing is that if A is consistent and one of U and A is sequential, then they are irreconcilable. So so you cannot extend them, you can never make them equal by extending them finitely, modulo mutual interpretability. So we have some kind of negative results for Friedman reflexivity. And so, I'm going now to demonstrate, to prove to you the second incompleteness theorem. So suppose U is Friedman reflexive and A is consistent. And so if they are irreconcilable, then we have the second incompleteness theorem. Well, why? Well, suppose A is consistent and suppose that A would interpret U plus the interpreter of A, then U, by the universal property of interpreters, A would be mutually interpretable with U plus the double diamond of A, and that's impossible, right? By irreconcilability. And so, so this means that we have G2 for when A and U are irreconcilable. And of course, so if one of the two is sequential, we know that they're irreconcilable. So if U, for example, if our base theory is sequential and Friedman reflexive, then we have the second incompleteness theorem. So the interesting thing is, so in general, you don't need to have the second incompleteness theorem. In fact, the provability of the interpreter logics, I should say, of these things could be S4 or K4-5. So you can have all kinds of things when you get out of the comfort zone. So the second incompleteness theorem does not hold everywhere. So I have examples of Friedman reflexive series that do not satisfy the second incompleteness theorem. But when you have the sequence coding, you're there. So the interesting next question to answer is what happens if you only have pairing, but I don't know that yet. Okay, so now I want to introduce you to, so the point, yeah, so if you think about Harvey's argument, so one thing that is a pity about this Peano is so strong, right? So this also means that our characterization of the consistoids is modeled over a very crude equivalence relation. And so can we get the same effect, but then in a much weaker context? And the answer is yes, of course, otherwise I wouldn't tell you about it. And so but there's a kind of interesting philosophical point behind this. So because there's this division between with parameters and parameter free, right? So if you look at Peano, that's really something like elementary arithmetic plus essential reflexiveness, right? So that proving the that every finite extension proves, that every extension proves the consistency of all its finite subseries. But the important point there in Peano is that we have the essential reflexivity with parameters. So it's not a sentential notion, but it's a notion with parameters. And in fact, the essential over, let's say, EA, the essential reflexivity of PA is equivalent to full induction. It implies full induction. So, and so that's what makes it strong. But if you think about, so the things we are thinking about now are all sentential. And so what you need is something like a sentential analog of Peano. And so, so, well, we need first a few definitions. So we take, we write box A and B. For B is A provable with a proof in which only formulas occur of which the complexity is smaller or equal than M. And I always use the very good notion of complexity, namely depth of quantifier eliminations. For many reasons, that's a correct notion to use here. And I will write the triangle AB for that B is provable from A with formulas of complexity that are adequate, so that both A and B will be in the range of the complexity bound, right? And so my triangle A is really cut-free provability, but I find it always more convenient to use to have some notion of bounded bounded provability. But if you read cut-free for it, it's okay. You could always also read Hairbrand provability or some such notion, right? All these notions are multi-exponentially related and could be substituted for each other in the present context.
Quick question.
Okay, and then
Quick question. In the box, row A implies B, A. Should A and row A implies B be reversed?
No, I don't think so, but it doesn't really matter because they have the same row.
No, I
Because
think
row
yes.
something is a number, and in
Right.
the notation upstairs, M is a number and it's on the right. That's why I asked.
Oh, okay. Sorry. Yes. Okay. Oh, yes. You're completely right. Yes, you're complete. So this is because in an earlier paper I had the complexity in the second place, and now in this paper I think I have it in the first place. Oh yeah. Oh, sorry. Yes, of course. You're completely right. That's why I hide it with a triangle. Then we don't need to worry about it anymore. And Okay, and now you see that you can define the notion of essentially sententially reflexive if there is an interpretation of S12 such that we have that U proves the reflection principle for all U sentences A, right? So it's really so in the case of piano, you have a box here and you allow free variables here, right? And this is now the sentential counterpart. And yeah, it's important here that we do not have full provability, but just cut-free provability. And and now if you think about Harvey's argument, you see it doesn't use the uniformity or the parameters at all, right? It's a parameter-free argument, and so precisely the same argument works for essentially sententially reflexive series, and so we do have here then that the double diamond of A will become the nabla, so that's my not triangle not. So it will be the cut-free consistency of A, right? So that's it. Now the simplest example that you could take is take some your favorite weak arithmetics or S12, but in fact the whole thing works with PA-2. It's I like S12 because we don't have to worry about the arithmetization of syntax and all those things. So if we simply take S12 plus all reflection principles for arithmetical sentences, then you get a series that I call pianissimo, and that's in some sense a kind of minimal series that does this. And then, but there's another series that's slightly stronger. That's piano that I call piano corto, or piano with the double down arrow. It's your base series plus all sentences that say S implies S relativized to a definable cut, right? Where the S ranges over sigma 0, 1 sentences, which have to be defined as first a block of existential quantifiers and then a delta 0 formula. And so by well-known tricks, you can axiomatize this in an effective way. And so now we have some kind of very good properties. So piano corto is essentially reflexive. It's locally cut interpretable in S12. So S12 doesn't interpret it, but it locally interprets it on deeper and deeper cuts. So that's the property, and it is even in the same way interpretable in Q. So this means that it's very weak, and as a consequence, EA will act really interpret it. But then piano corto proves the same, even if it's so weak, it proves the same implications of pi 0, 1 sentences as EA. And yeah, what I thought is most amazing, even if it's so weak, it's in none of the I sigma n, right? So it's not in your usual hierarchy. It's not, you cannot place it there. And yeah, so the interesting thing is so that even if it's very extremely weak, it is in many senses more PA-like than the I sigma n. And so in slogan, in logic, there's more under the sun than strengths. Now we have some good properties. So suppose that you have a P pi 0, 1 sentence, and that is an interpreter of A over piano corto. Then we have, by the uniqueness of by the uniqueness of interpreters, then we have that piano corto proves that the equivalence with the cut-free consistency of A. And so So by the result about the connection with EA, with elementary arithmetic, we have that EA proves that P is equivalent to the cut-free consistency of A. In fact, we have also the implication back, right? It's in fact if and only if. And so we have characterized the cut-free consistency of A among pi01 sentence modulo EA provable equivalence, right? So that's my promised improvement of Harvey's characterization of the consistency statement. I get it now modulo EA provable equivalence. But you see that here, so the natural thing is really cut-free consistency here, where so Harvey had consistency, but over Peano we couldn't see the difference between consistency and cut-free consistency, because Peano, or even if we would add to Peano corto super exponentiation, then the difference will disappear, right? It's just that we are below super exponentiation that this difference happens. And we also have so we know the Friedman characterization for EA, but we also have the Friedman characterization for Peano corto. Why is that true? Suppose A interprets B, then S12 plus the cut-free consistency of A improves the cut-free consistency of B on a cut. So why is that? Well, if there's all kinds of, there's no end of ways to prove this, but one way is to say, suppose we have an interpretation K, then, so if B, now take a bound that is large enough, let's say a big M, and so then we can, so suppose that B, so suppose that B proves its own inconsistency with bound the complexity of B, then we can use the interpretation to find an inconsistency proof of A with bound some big M, right? So because that you use, of course, that we have the interpretation, and we need the argument in A, you inside the interpretation, so that adds some overhead. But then, of course, in S12 we can find but we can restore this big M to a row of A by if we have a sufficiently high tower of exponentials, and of course that is what is provided by going to a deep enough cut, right? So that's the idea. So if we have this inconsistency, the cut-free inconsistency of B for its own row on a sufficiently deep cut, then we have the inconsistency for A for a big M. And then since we choose the cut deep enough, we can do cut elimination for the sufficiently high tower of exponents, and tada, you have the row cut-free inconsistency of A, right? So that's one argument way to do it. And the other way around is so if suppose that we have S12 proves the cut-free consistency of A and implies the cut-free consistency of B on a cut, then so we have that A interprets S12, since A is sequential, it interprets S12 with its own cut-free consistency on a deep enough cut of some choice for the numbers there. And so, but then that theory proves the cut-free inconsistency of B on a cut. And then you apply the interpretation existence lemma to find an interpretation of B. And so putting everything together, we get A interprets B. And So now for the second, if and only if we apply the fact that S1, that piano corto is locally cut interpretable in Q, right? So, so if S12 proves cut-free consistency of A implies cut-free consistency of I on the cut, then by the definition of PA corto, it will prove the implication without the cut. But the way back is, so if piano corto proves that implication, so here, then you have this implication on a cut in S12, and then so a fortiori you have that you have cut-free consistency of A implies the cut-free consistency on I, and that implies the cut-free consistency. So we have nice Friedman characterization that interpretability between finite series is equivalent to provability of relative cut-free consistency, right? But it's important so you do not get it when A is not sequential. So there is regrettably a condition. So it's a version of the Friedman characterization. And in fact, it implies the Friedman characterization, and the Friedman characterization also implies it. Okay, so now I still have 15 minutes or something for some of the real action. So, but now, of course, so the interesting thing is, so what now can we characterize? Can we characterize sequential Friedman reflexive series? Okay, and so and the answer is yes, we can. And you do it like this. So start with our sequential series, and suppose that we have an interpretation of your favorite arithmetic, and let ij range over cuts of this this interpretation. In definable cuts, I always mean definable cuts there, and let S range over sigma 0, 1 sentences. And then we have our characterization that, of course, is reminiscent of the definition of piano corto, but there's a subtle difference. So U is Friedman reflexive if for every S we can find an I dependent on S, such that for all cuts J we have U proves SI implies SJ, right? So the whole thing is, so in piano corto, where is it, this thing? Where's the definition of piano corto? Oh yeah, here. So you see that it's a fixed, you have here we have a fixed thing, the identity, and then it implies that there are smaller and smaller witnesses for S. And here that it's the same, but the starting point need not be constant, right? So we can, so only if we have S, so we need a sufficiently small witness to get the process of smaller and smaller witnesses going. So that's the basic idea. And so you can take then the interpreter of A to be the cut-free consistency of A with respect to the cut that is provided by the characterization, then for the cut-free inconsistency of A in the role of S. So the whole thing is that interpreters are not precisely cut-free consistency statement, but they're arithmetic hopping cut-free consistency statement. They need not be in the same place all the time, so they can change where they are. Okay, but I will say more about the kind of the heuristic for this, which is in a way that it will more speak more to the model theorist in a moment. But let me first say, in the end, maybe it was not very difficult, but I stared at it a long time to find a real example that this could really happen. But indeed, you can construct an example. I call it U, the theory U, but then not italic U, but sans serif U. such that the IS, so the cuts that you associate with every sigma sentence are forced to be smaller and smaller. So so you will be not essentially sententially reflexive. So you can find a real example of this this happening, and you can also show that. So there's no. So this is a kind of real difference with our usual consistency statements. We can show that we cannot overuse, we cannot characterize the interpreters uniformly by a predicate. So there is no formula C such that we have C of the Gödel number of B if and only if we have the interpreter of B, of the consistoid of B, or the double diamond of B for all B. Yeah. What I don't know, which is kind of connected to questions that I've been discussing with, for example, Matthäus, is so if we interpret U in a finitely axiomatized theory, can we then find in the finitely axiomatized theory at least a D that does this? I simply don't know. So it's a really open question. But so the second characterization will explain a little bit better what the idea means. So suppose, yes, consider any sequential model M, right? So that's a model in which we have sequences, good sequences for all objects, and fix an internal model of our favorite arithmetic, let's say S12. And now we take I of M, or the fracture I of M, to be the intersection of all definable M cuts. Of course, so note that that's a second order notion, right? So we cannot generally define I of M in the model itself in a first order way. So now the interesting thing is that I of M is unique in a very strong sense. So so it's independent. It's independent of the choice of N. So take any other such internal model N prime, and so now then we take the I of M, but then with respect to this N prime, and then the whole point is that it's definably isomorphic to the other IM, but also all definable isomorphisms for these things coincide when we restrict them to IM. So there's really a unique isomorphism between IM based on N and based on N prime, as long as, of course, we look at definable isomorphisms. So it's of course, this is just Dedekind's argument for the uniqueness of the natural numbers, but then taken to a new context, right? Also, because if you have two number systems in the Dedekind thing, not only are they isomorphic, but also there's just one isomorphism between the two, and that's the same here. And so, if you think about it, you can see that this IM. So the whole point is, so in the sequential model, we need not have any internal thing that satisfies exponentiation. But if you take the intersection of all cuts, then suddenly you do have exponentiation, and you have a sigma collection, and of course much more, right? I'm not saying that is all you will get, but so IM is really a very comfortable arithmetical theory, so much more. So here we have things like Russell arguments, etc., but that we didn't have, don't need to have here. And so now let U be any sequential theory, and now we take U extended to be the set of all A's in the U language extended with a new symbol I, valid and all U models M in MIM, right? So this is a second order thing, and it's so we could. I don't have an example, but at least it's in principle, it would seem possible that where if the given theory U is an RE theory, that UE is not RE anymore, right? So it's not. It's of course the characterization of the thing is not first order. And now we have here the second characterization. So suppose U is sequential, then it's Friedman reflexive if for all sigma 0,1 sentences S, there is a B in the U language such that UE proves that S relativized to I is equivalent to B, right? So the whole thing is, so the Friedman reflexivity really means precisely definability of the sigma sentences when restricted to J in the original language, right? So it's a reduction. So the whole theory UE is in some sense essentially second order, but we have a reduction or a window. So the Friedman reflexive series have a window on the sigma sentences on the new objects I. And of course, B can always be taken in the form SI for some anchored I, right? And so the consistoids, the double diamond of A is of course precisely the cut-free consistency of A restricted to J. And so, yeah, it's a pity because I cannot treat provability logic, and so you really need to get to really get a feeling of what this means. You have to do the Soloway argument. But interestingly, so this J, this class, internal class, functions really as a kind of point of infinity you add to U, and the Friedman reflexivity really says that you can see what Boolean combinations of sigma 0 sentences do in J, right? So it guarantees that this given theory can see what happens in J, at least as far as the Boolean combinations of the sigma sentences are concerned. So yeah, it's a substantial shadow. So it's a more substantial shadow than you would have in the non-Friedman reflexive series. Okay, so that's that. And in fact, we have still a little bit more, and that's the fixed point lemma. So suppose U is, so for the, yeah, interestingly, for the fixed point lemma, I seem to need that it's effectively Friedman reflexive. So I don't have a refutation that you don't get it when you drop the effectivity, but I seem to need it. So, so take any Boolean combination of sigma formulas with only x free, then you can find a D in the U language such that U of E proves D if and only if BD, but then the BD relativized to I. And so that's so that, yeah, this is so this allows you to extend classical mathematical proofs also to the Friedman reflexive series. Yeah, so what I wanted to say is that, so it's really a pity to see this in action. You have to see the proof of the Soloway theorem, and only for speaking for myself, I only really understood what these things mean when I was looking at the Soloway theorem, because there you can see every component really comes into action, and it's so you really see how the usual arguments translate using these insights. But regrettably, time is almost up. I cannot do that, and I haven't prepared it either. Okay, so now the last thing, is this the last, my slide? Yes, last slide. So now we can develop the analog so of provability logic. And so I did a lot about, there's a lot of stuff about the provability, well, I call this the interpreter logic of a series A. And so the basic data, this chat says something. Okay, Matteo, see you. Yeah. Okay, so what's going on here? Yeah, so how are we going to do the interpreter logic? How are we going to define the interpreter logic of a finitely axiomatized theory A? Well, the way, so if you think for a moment about provability logic of ZF. So how would we do that? Well, there's really two ways to do that. One way is we can do the arithmetization straightforwardly in the sets. ZF provides sequences, pairs, etc. And so we can do the whole arithmetization directly in ZF. But it's and that's in fact very convenient way to do it, because it's even simpler than to do it in PA. But doing it in, for example, PA is more efficient because we can do it for a lot of series at the same time. And so what you then say is really, here we have CF. It has the von Neumann interpretation of Peano on the finite von Neumann ordinals. And we have arithmetization, etc., on the finite von Neumann ordinals. And so we can simply borrow provability as developed in Peano in ZF using the von Neumann interpretation, right? And so the format there is we have an interpretation of Peano in ZF, and so the provability in ZF will be the ZF provability as formalized in Peano, then relativized to this interpretation. And so that's the format, right? So to borrow your notion of provability from another series, you need an interpretation. And so that's what we do. So we take an interpretation K of A in U. So note that we have always been looking from interpretations of A in U, and now we look at an interpretation of U in A. We have to start with, we need an interpretation of U in A. So U is the base series and A is the main series. And we ask now that U is reflexive. And now we can develop the interpreter logic of A given K, right? So the K is really the basic datum for this logic, this interpretation, because it has A and U as data. And so interpreter logic can be there of all kinds that I already mentioned this. It could be S4, it could be K4 or 5, and some extent Loeb's logic. And now one can show that if either A or U is sequential, then the interpreter logic will extend Loeb's logic, right? So as soon as for example, the base series has sequence coding, then we get Loeb's logic. And of course, this is a little bit disappointing still, because I would hope to get this for if we would have something like pairing, and but yeah, so that's still under construction. And so now the whole thing is that if it's effectively Friedman reflexive and sequential, then we have Solovay's theorem. So and interestingly, this works even if the relevant provability analog cannot be represented by a predicate, right? So yeah, it's a little bit of a pity, because why doesn't it work? So the whole thing is, so as if you try to prove Solovay's theorem, then you can see the intersection of all cuts as a kind of natural object in action to prove a real theorem. And so yeah, the heuristic is simply this, right? So if you solve a theorem, it's all about Boolean combinations of sigma sentences. What you need to do it is exponentiation, so we don't know how to do it in S12. And what we need is the fixed point lemma, but only a fixed point lemma for certain formulas of restricted complexity. In fact, the fixed point lemmas for Boolean combination of sigma sentences. And so that's the reason that the whole theorem can be miniaturized or recovered in the context of the Friedman reflexive series. So that is precisely what the I intersection of all series delivers. Okay, that is it. That's it.
Okay, thank you, Albert. Let's all thank the speaker. And let's take some questions. So if anyone wants to go first, please feel free to.
I got in a bit late, and I wouldn't mind seeing the first 4 or 5 slides with the definitions. I was sort of inferring them, but
Wait.
just what those symbols mean.
Oh, the framework, right?
Yeah.
Yeah. Okay. Yeah. So
Well, everything before, I think I came in around 4, but
right. Yeah. So the whole thing was that interpreter is in some sense over the given theory, the interpreter is the weakest statement. The interpreter of A is the weakest statement over the given theory that interprets A, right? So that's what this says.
so what does that, I mean, so that symbol, that triangle symbol, is that defined in the earlier slide? That's a symbol in what language? That's
yeah, right. So this symbol here, so the double diamond is really a column function that selects an element of an equivalence class, right? Because the interpreter is uniquely defined. Yeah, we could also set it up such that it really, but I find that a little
but
bit
above that, even that triangle on its side, whatever you'd call it.
Right. So that's
interpretation.
So this really means
that's the existence of it. Are you quantifying over interpretations or something? Or
yeah,
or
right.
what?
This means there is an interpretation of A in U plus B, right? Or U plus B interprets A.
Interpretation in the sense of translations of syntax. So there exist formulas in the language such that this, that, and the other thing.
Right. So there's
So just the existence of an interpretation, and then but not attempting to distinguish between them or anything like that.
No,
when
right.
you're making categories, this just makes it this collapses a lot of things, right?
It is the weakest category, right? It's the category that is a degree structure. Yeah, precise. We don't have interpretations as
particular to partial order, I guess.
Yeah. Partial pre-order. Yes, precisely.
Right.
And so the point is, and so the interpretations can be more dimensional, right? There could be some extra features that make them a little bit more flexible. So they could be more dimensional, or they could chop up the domain in pieces, blah blah.
And
so
then was there anything else on those earlier slides? S12 or something, or was that on the later slide? I just don't know.
That's later.
Slides 1 and 2. Maybe it was just a picture or something. But
okay, so then we have this notation, which is the consistoid of A, or the interpreter of A, or the double diamond of A. That's that. So then, now here we have no new. So S12 is Visser's theory for p-time arithmetic. But if you're more as a model series, you're probably comfortable with PA minus or some other weak theory. And so, but PA minus doesn't have PA minus doesn't have or Q doesn't have a good treatment of syntax, and so the S12 has the advantage that it has a good treatment of syntax. That's why I choose it as the base theory. But in fact, because you have a lot of Q, we have Q, PA minus, we have I delta 0 plus omega 1. So so omega 1 is that 2 to the log x squared exists. So all these series are mutually interpretable, right? So there's there. So you could use a different series here.
Or something like I delta 0. That's all I have to know. I mean,
Yeah, it's something like I delta 0, but it's guaranteed to be finitely axiomatizable. That I like that as a property.
I see.
And for I delta 0 plus omega 1, it's still an open question whether it's finitely axiomatizable or not. Okay, and so the box I use for ordinary provability. So I is relativization either to an interpretation, but here simply to a cut. And a cut is a definable cut.
Definable cuts, right? So again, yeah.
Definable cut, and my cuts are closed under plus and times and preferably under omega 1, which is again to the log x squared. And they are downwards closed. But yeah. Let's see. So this one is, of course,
what was that last thing closed under, and then that was that function? You're closed under.
Oh yeah, so omega 1 or Bus's smash function. So omega 1.
Yes, what is that? I've seen that in context, but I've never quite understood this. So when you're in a system of very, very weak arithmetic, you don't have what this is less than assuming exponential growth, right?
Yeah,
it's
much less
like
than
at the limit of what you need to express syntax and so on.
It's precisely so. If you do your arithmetization, your Gödel numbering in a clever way, right? And the clever way is simply the length
like a
first
computer
ordering.
scientist or an engineer or something, yeah.
Yeah, right. You know, so you order the strings in lengths and the strings of the same length alphabetically. So then you number them. That's the length first ordering. That's a very good Gödel numbering. And then the point is that so concatenation has the if you translate it to numbers, back to numbers, concatenation is going to be roughly of the order of multiplication. But you want also substitution. And so the real thing to think of is that the omega 1 function is really substitution under this back and forth translation. That's the right heuristic. Right, so if you want to develop syntax, you need substitution, and that's why omega 1 is so present to have. Right, that gives you p-time computability. It's slightly stronger than multiplication, but far below exponentiation.
Mm-hmm.
And in fact, so if you start with q, you can interpret I delta 0 plus omega 1. But if you start with q, you cannot interpret I delta 0 plus x. Exponentiation is total, right? So exponentiation is, that's a different story.
I'm sorry, what was that? You can't, well, maybe, I mean, someone else should ask questions. I don't want to just.
Right, so okay, so the point is, so this omega 1, so there's all this work by Paris and Wilkie and Putlak and Solovey, and so the whole point is that this function omega 1 are an even faster function, like 2 to the log x squared. That's even faster. That's omega 2. So all these functions can be interpreted over, let's say, PA minus. Right? You start with your favorite weak series, and you can interpret faster and faster functions. But you never can reach, you can prove that you can never reach elementary arithmetic, so I delta 0 plus exponentiation, because exponentiation is something really new that you cannot reach using interpretations from the weak series. Okay. Yeah, and so this one means mutual interpretability. So it's interpretability in both directions. So I like the bow tie as a symbol for that.
But with no a priori relation between them. No, not that they're inverses or anything like that, right? Just
yeah, right. You in both sides you quantify out the concrete interpretation.
Right. Oh, that's right, you've already done that, so, yeah.
Yeah, I think these are okay. And now the triangle, yeah, you were there when I introduced it, right? That's really cut-free provability.
Yeah, with the subscripts reversed, right?
Ah, yeah, sorry about that. Oh,
So that part I got.
yeah, very good. And so, yeah, I think that's all of it for I think that's all of it qua new symbols, I think, right? Everything I did introduce. Of course, this is just hand waving towards this the provability logic, right? That's a big, that's in fact the main part of my papers at the moment. So I just hand wave. So I just wanted to tell you this also exists.
So am I to understand that throughout cut-free proof does not have anything to do with Gensen's cut elimination theorem?
Yeah, it has.
It has, okay.
Because the point is, yeah, so if you, because the point is, so if you have, yeah, where do I have the thing cut-free?
Yeah, cut-free consistency comes up often.
Yeah, right, here it is, right? So the whole thing is that if you have cut-free consistency, right? It is of course not the cut-free thing of Peano, right? It's just for predicate logic that we're using here. And so you have you have the sub-formula property. And so the whole thing is that a cut-free proof, so a bounded proof can be, so if you have exponentiation, then a bounded proof where the bound is standard can be transformed into a cut-free proof by cut elimination, because cut elimination is multi-exponential in the tower of the tower of exponents for cut elimination that needs your bound, right? It's I never remember it precisely, but it is some linear term in this bound, and then there's a 2 to the 2, and then there the proof is on top, right? Or maybe also the proof times a fixed finite constant C or something like that. But it's in fact, yeah. So if you have EA, then we can, for the bounded, so as long as your bound is standard, you can do cut elimination in EA, right? You cannot do it generally, because that you would use super exponentiation, because then if you do it generally, the tower of exponents would grow, and that EA cannot do. But EA can do the cut elimination here, right? So over EA, this thing of mine is really cut elimination. And if you take other formats for cut-free provability like Herbrand, they're all multi-exponentially related. So all these things are translatable into each other over EA. So that's the point. And so yes, it has to do with cut elimination, even if I never use cut elimination. Well, in this argument I used it. Where is it here? But I think I know how to avoid it, because I did use here a little bit of cut elimination to get from the B proof of falsity to the A proof of falsity using the interpretation K that was given here, right? So, but that would blow up your bound to a big M, and so we have to reduce that M, and that reduction of that M that introduces the cut here. So yeah, there I did cut elimination, but I think I also can think of an argument without cut elimination.
I think behind Ken's question is the fact that the word cut is being used here with two entirely different meanings. In fact,
yeah, that's a legacy problem.
Right.
It's like I cannot help it. It's not my fault. I know, but it's legacy, right? It's not an elimination of definable cuts or anything like that. Yes.
But I wanted to ask at the beginning, you mentioned the ambition of finding Gödel type sentences which do not depend on an arbitrary coding, like parameter
Yes.
free.
Yes.
But you're not claiming that this stuff here does that, right? Because your double diamond still involves coding.
No. No, they don't.
Oh, I don't. No, okay.
No, so of course, there's all kinds of problems with the double diamond. So the program, so there are no magical elixirs in meta mathematics. But for example, for the simple case of piano, they don't involve any coding, because so this equation. So if we take piano here, and if we so this equation really uniquely defines the consistency statement, right? Without talking about coding at all. So it does that. So this thing is does not have a hidden thing about. So it's not a predicate of a Gödel number, right? It's a Skolem function that picks an element of an equivalence class, but a random element. And of course, I could also eliminate that. But I think it's ponderous, right? We could say that it's a function from equivalence classes modulo provability to equivalence classes modulo provability, right? So we could view it as a function on equivalence class, but I think it's I myself find it very pleasant to think about functions on sentences, so that's why it's a Skolem function. But yeah, but I guess you could eliminate this if you object to that, and think entirely modulo provable equivalence. But modulo, yeah. So the point is, so we can do with for good cases like piano arithmetic. And for example, piano basso, we can do without coding, right? So it's important to realize. So this is coding, no coding in the formulation of the theorem, right? It doesn't mean that the proofs do not involve coding. That's so it's like it's like for example, if you think of the second incompleteness theorem, so the formulation of the second incompleteness theorem is self-reference free, even if the proof does involve self-reference. And in the same way here, the formulation of the theorem is coordinate free, so we don't have to say at all what consistency is. So for example, the consistency statement of PA is really the same as the consistency statement of ACA 0. And so there you see the formulation of the whole thing. So we can define the consistency of PA in PA without any coding. At least I would, of course, to formulate ACA 0 in a finitely axiomatized way, you need to get the finite axiomatization, you need to do something with the pairing, right? You need to find some axioms using pairing, but I think that's not really, I wouldn't count that as coding. So if you think the usual formulations of ACA 0 are arithmetization free, then we are home, right? We can define the provability logic of PA in PA without any arithmetization. Yeah, it's good that you asked that, so I can drive the point home that indeed for a large class of cases, this indeed does work and delivers, as promised, a coordinate-free thing.
You've just made, I mean, I think that's an important point you're making, and you've just made it, but maybe could you make it again in a more elementary way from the beginning? I mean, maybe that's what you said on the first slide or something, but I've seen this in Harvey's posts about formulating the incompleteness theorem in via interpretability.
Right. Yeah.
And
right.
The most basic version of that is probably what's motivating all of this.
Right, that's this one, right? So this motivates, so So the
Okay, so that
Of
did
course.
come in. So this says, all right, so suppose A is finally axiomatized, and this is what, in any language, any signature or something, and then you just take it together with PA or what? Or are you, or just within arithmetic?
No. So
Or-
the point is, so here you see the concrete, right? So we have the base series PA, and we see the
Yeah.
concrete characterization.
Okay, the
of-
base theory is PA, right? Okay, which is not so weak. Okay, yeah,
Yeah,
so,
but that's not very weak. And so, but then the property we need is simply this
this
property,
property, right?
And then
Right, and
and
so you get this from PA basically because you can arithmetize syntax is your point, right? But you can hide the details of that in this assertion.
yeah, the point is, so the proof of this, yeah, that's
Right.
pretty. So you see, so this characterizes the consistency statement in a completely coordinate-free way, right? So here, the explanandum here, but that's the explanandum. That is this. Here you have the arithmetized thing, but you can eliminate it because it is the unique C that fills this. So if I replace this by C, then the universal arrow equation tells us that the C will be provably equivalent to this, right?
Right.
So
Up to choosing a particular one of those, which we don't care
yeah,
about.
and this is just a particular one of those. But yeah, this illustrates, of course. So here you see that in the proof, I of course use arithmetization, etc. Right? So it's not eliminated from the proof, but it's eliminated from this. You can eliminate it from the statement.
Because I guess all those details are relevant when you prove essential reflexivity.
Right.
Or
And so,
something like that.
so
Right, yeah.
here you have the.
Sure.
So here you have my general version of the incompleteness theorem, right? So, so first, the very general thing is this notion of irreconcilability. That has nothing to do with arithmetization, right? It's this. So it holds for any series V and W. We can say what it means that they're reconcilable or irreconcilable. That's the negation of reconcilable, of course. So they're reconcilable if you can extend them both in such a way that you get mutual interpretability. And if you cannot do that, they're irreconcilable. And so then the second incompleteness theorem follows from irreconcilability. So that has not, this statement has nothing, and so both statement and proof are completely arithmetization free. But now the application, so are there interesting pairs there? And so that's the case, that's sequentiality, right? So if the base series is sequential or the main series is sequential, in that case, we do have G2 because if one of the two is sequential, then we have irreconcilability. But
Sequential means you have some machinery to handle sequences. You can talk about sequences and concatenation and things. That's one of these definitions I've been meaning to chase down for a long time. But
right, yeah. So I gave many talks with introductions to that, but it really means that you have sequences in the strong sense that you can concatenate them, etc. Right? So
where sequences have the sequences have lengths, and lengths are the natural numbers of your theory, and that sort of thing.
Yes,
okay.
precisely. And you can concatenate the sequences, and you can have projections, etc. Right? So that there are very short, extremely short, elegant definitions of sequentiality, but then it's a lot of work to get from that definition to all the properties you want.
But that's always, I mean, sequentiality, that's always in the context of the language of arithmetic, or is it a more general?
No, completely general.
So how is the length expressed if you don't have, or you just sort of tack on the language of arithmetic?
Yeah, well, you prove that you have, yeah, well, okay, there's this simple set theory. So that it says that there's no empty set, And given that you have some set, then there you can adjoin an element to the set, right? So that's called adjunctive set theory. And you don't have extensionality. And so the theory is sequential if and only if you can define a binary predicate in the theory such that that has the properties of this extremely simple set theory. And then it's a very large bootstrap, so running over a number of pages to prove that in this theory we have sequences of all objects, and then that we can define the natural numbers on which you have S1, 2.
You first have to get pairs, and then you have to get ordered pairs. You just sort of redevelop set theory.
You redevelop, and there's a lot of shortening of cuts there going on, etc., right?
I'll Google. I'll do some searching for that. But yeah, no, that's good. That's. And my discovery, well, a piece of wisdom is you should do it yourself. It's impossible to read what another man did. You really should do this for yourself. It's as with reading a computer program. It's often much easier. What I've been wondering, I have my own pet application, which is not worth discussing here, but what I've been wondering, and I'm not a logician by training, right? So this could be a daft thing to wonder about, but some discussion where you could talk about arithmetic, let's say piano arithmetic, but it could be a weaker theory. A piano arithmetic, at least I know what it is. And then at the same time, or something that's equivalent to that, at least for the purpose of talking about sequences, but sequences of what? So for me, I'm interested in sequences of say real or complex numbers because I'm interested in algebraic geometry. And I'd like to think about some elementary theory, which is it's elementary in the sense that everything has to be definable in this language. But on the other hand, I can still talk about quantify over dimension and talk about n tuples of different lengths and so on. And I don't know. Anyway, I mean, I can imagine how linear algebra looks that way, but I'd like to know, I'd like to see how much algebraic geometry does. And it's not just the same as saying Lefschetz principle, because we want to actually prove things formally about the length. Anyhow, that's a distraction. If you know anything about this, I mean, I've tried the internet searches for a while. There's a couple of actual questions I have specifically about this.
As soon as the theory you have is decided, so the point is the sequential series are all essentially undecidable, right? So they're
well, that's okay. That's okay. That's okay. I know. I mean, we're starting. It's this discussion here. For any given dimension, it's decidable, and the whole question is whether or not you can prove that in some uniform way and express that uniformity somehow as a formal statement in arithmetic. And I don't know if anyone has actually seriously invested. I mean, there's a handful. There's the 1, 2, 4, 8 theorem about division algebras. And this is noted by Kreisel even years ago. And I don't know. I mean, I had some. I asked this in FOM like 25 years ago. But anyhow, I just simply don't know if this is a mathematical question or not. But whenever I hear about sequentiality, and then it doesn't have to be arithmetic, this comes to mind.
So the important point of sequentiality is that at least it's sequences of all. The really important thing is sequences of all objects, right? So including the sequences. It's
right. Well, sure, because of course I have matrices, right? So if I have vectors, sequences of vectors are matrices and so on.
Right. Yes. So it is really sequences all over, and it's also with variable. So you have to be able to speak about variable sequences of variable lengths, and not because there's also something called Vaught set theory that is weaker, and there you can talk about sequences of any length n, but then the length in some sense is not variable inside the theory, but just for us in the meta.
No, I actually would want the length to be something in the theory.
Yeah.
Not just in the meta theory. I mean, I can just sit out. I mean, you can in the meta theory, you can just say Lefschetz principle, but then that's not what I'm after. Anyhow, I'll do a little bit of searching on that. Thanks.
But I'm sorry that I don't know the answer to your question.
No, I haven't really. I didn't come to this talk prepared to ask that question, but you did. You lured me in with the coordinate tree, that language.
Right. Yeah, of course, the coordinate-free idea is by itself an old mathematical ideal, right? So
It's the hill I choose to die on. That's a private
Yeah.
joke.
Okay.
Yeah.
More questions.
Okay, so I think let's thank Albert again, and I'll stop the recording here.